One of the most important factors in providing plants adequate nutrition is starting with good water quality. Proper plant development depends on as pure an environment as possible. This includes a clean, toxin-free water supply. This community stream shows a few obvious problems. The vegetation doesn't look healthy. There appears to be some sort of film on the water surface, and trash is seen in and around the water. It is likely that this storm drain has been misused by some people in the neighborhood. There's evidence of oil deposits, rust, and the stream most likely contains other contaminants as well. A water analysis should be performed before using this water for hydroponics. A standard water analysis will measure pH, alkalinity, and conductivity, and also shows concentrations of calcium, silica, and phosphates. Analysis of major and trace elements should also be performed, especially if conductivity is high. Based on analysis results, water purification, such as reverse osmosis, may be required. Another important factor to help ensure healthy plant growth is to aerate the nutrient solution to increase the oxygen content. Adequate oxygen is needed to maintain healthy roots, which allows for sufficient nutrient absorption to the entire plant. In this ebb and flow system, aeration is promoted in 3 ways. Number 1 is the turbulent action of the water as it passes through the flood and drain fitting. Number 2, when the nutrient solution reaches the desired level in the growth container, it is dumped back to the nutrient solution tank. This action traps more air and forces it into the nutrient solution. Finally, to increase the oxygen level even more, an aquarium air pump is installed to continuously bubble air into the solution. This subaeration experiment proved that a plant can flourish with essentially no growing media. This tomato plant is provided a balanced nutrient solution with a constant supply of air. And, as you can see, the plant is doing quite well. Another very important factor to plant growth is controlling the pH of the solution. pH is the measure of the acidity or alkalinity of the solution. The pH scale ranges from 0, which is highly acidic, to 14, which is highly alkaline. A pH of 7 is neutral. Most plants do well in a pH environment of 5.5 to 7.0, slightly on the acidic side. A pH of 6.3 is widely considered to be optimum for most plants. Note on the graph that beyond the normal pH range, either more acidic or more basic, certain minerals become more or less available for absorption. The nutrient solution then becomes unbalanced and becomes either deficient or toxic to plant growth. There are several ways to test pH level. Perhaps the easiest method is the use of pH test papers. This test has a fairly narrow test range, but is reasonably accurate. To test, simply tear off a piece and dip into the solution. Remove quickly, then immediately compare the color to the chart provided. This pH appears to be approximately 6.4. Another slightly wider range test method is the use of bromothymol blue test liquid. This is basically the same as aquarium test fluid. As you can see, the range is wider and colors more vivid, which makes it preferable to the test paper method. To test, fill the provided test vial 1/2 full and administer the recommended amount of fluid. Apply the vial cap, shake gently, then compare the liquid to the color chart. Once again, we have a pH of between 6.0 and 6.5. Perhaps the most accurate pH device is the electronic pH test pen. The pen consists of an LCD indicator, a wet bulb, and electrode sensor. This setup actually measures the hydroxyl ion concentration, which is the basis of pH. Measuring the same test solution as before, we now have an indication of 6.3. If calibrated properly, this is an accurate indication with only a small error factor. The pH of the nutrient solution can be adjusted either up or down by using the appropriate fluid. When correcting pH, always use a small amount of the correction material, wait several minutes, then test again. Then add more if needed. But above all, follow directions. Use caution when dealing with these correction fluids as well as all other fertilizers and supplements. It's always a good idea to use gloves and eye shields when using any of these materials. pH pen calibration solutions are available to calibrate both lower and higher pH indications. pH pen accuracy should be checked often and calibrated when needed. When not in use, the pH electrode should be placed in a storage solution. This is easily accomplished by merely placing it in enough solution to cover the electrodes. If the pH pen has not been used for an extended period of time, the electrode can be reconditioned by placing in a storage solution for about an hour before using. The TDS meter measures the total dissolved solids, which represents the concentration of dissolved minerals in the nutrient solution. The concentration is indicated as parts per million, or ppm. Very basically, the whole thing is accomplished by an electrical current passing between two electrodes submerged in the nutrient solution. This is called conductivity, which is the ability to pass current and increases with the increase of dissolved mineral salts in the solution. Similar to the pH pen, the TDS meter has an LCD indicator screen, a switch, and sensing electrodes. Nutrient TDS requirements will vary according to plant type and stages of growth. For example, low-energy crops such as lettuce and most herbs do well at a TDS of between 500 and 800 ppm, tomatoes between 1100 and 2500 ppm. Start according to nutrient manufacturer's recommendations, then adjust as experience dictates. The TDS pen is calibrated similar to the pH pen. Simply submerge the test probes in the calibration solution and adjust. Remember to always rinse the electrodes with distilled water after calibration. pH, TDS, and reservoir temperature can be monitored around the clock with this type of equipment. This is very convenient, especially for larger, more permanently located systems. This system consists of an indicator panel, a pH probe, and a combination TDS temperature probe. These are left in the reservoir and removed for calibration and cleaning if needed. Well, that's about it for nutrient management. Join us in Chapter 3 for information about seed germination and cutting root propagation.